So today I want to try my hands on explaining this problem 3525, find x value of array 2. So this is a pretty tough problem and like I was not able to think of the key idea behind it. So for that the credit goes to a channel called Programming Live with Larry. So maybe you guys would have heard of it. Uh, he codes in Python most of the time, but like if you get the idea, it becomes a very I won't say basic, but it becomes like a segment tree problem. So let's try to understand it. So first of all, the even the problem statement is a little confusing to understand at first. Let's go through it. So I'll go like try to explain the problem statement using the example itself. So this is the nums array. You're given k equal to 3 and you're given a bunch of queries, right? So I'm just going to take the first two and try to explain it using that. 3, 3, 3, and 0. Okay, so what you got to remember, a query in this case is of the form uh, index, value, start, and x. Okay, I'll come back to what all this is in a minute. So you're given this array and you're given a bunch of queries. Now you're supposed to return a integer array of the same size as the query's length, right? So for each query, there's an answer. There's supposed to be an answer, and this result is just that. So maybe A, B, C, and D, right? Now, what you're supposed to do is, given this nums array, at first step, you're supposed to update the value at index 2 with this value, right? So after this update, like the update of the first query, your array will become something like this, right? So you've just updated this value at index 2 to new value 2. Now, what is this start, right? So what this question is saying, given this start, remove that prefix from this array, right? So in this case, it was 0. So you're supposed to remove everything before index 0. In this case, it's an empty prefix, right? And then you're supposed to, for all suffixes in this array, so suppose this is the array after pre, uh, removal of prefix nums uh, 0 to start minus 1, right? In this case, it was minus 1. So what they're saying here that num 0 to minus 1 denotes an empty prefix, right? So this is the array after removal. Now you're supposed to choose any uh, suffix, right? You're supposed to remove a suffix and you got to give the count of the number. Uh, okay, let me rephrase this. So let's just write down all this after removing some suffixes. Let's write down the number. So it's 1, 2, 2, 1, 2, 2, 4, 5. So I removed an empty suffix. Next, I remove suffix 5, right? 1, 2, 2, remove suffix 2, sorry, 4, comma 5. Then this 2, 4, 5, remove 2, 4, 5 suffix, and so on and so forth. So at the end, you'll have one. So you're supposed to have at least one element in that suffix. You can't just, in the remaining elements, you can't remove everything and have this empty. So the question is asking, if I multiply this, what is the uh, product here? Okay, so first I remove nothing, right? So what is the product here? The product is 2 into 2, 4, 16, 80, right? In this case, the product is 2 into 16. Here the product is 4, product is 2, and product is 1, right? Now this k value that's given, just take the modulo of that. So 16 modulo 3, in our case, k is 3 in this example, so that's 1, right? Modulo 3 is 1 again. Modulo 3 is 2, and modulo 3 is 1. And for this product 80, modulo 3 is 78, it is 2, right? So this x value is just this, like the remainders after the product of this whole thing, modulo k, and you're supposed to give the count of uh, these leftover arrays after removing certain prefix and certain suffix. The count of arrays which will give uh, the modulo k, the product modulo k as x. So in this case, there are two subarrays, right? This and this. So that's the answer for the first query. So if you see here, it's like remove the suffix 245 and this is 2, right? Similarly, you do the same thing again and again, and the value from this will persist. All this won't. Just this update value will persist, and then you move on to the next one. So technically, you're supposed to uh, give the count of subarrays whose product modulo k is this x value for each query after a certain update, which is from the first two indices. Okay, so that's the question. Now let's try to figure out how we can achieve this. Give me a second. Okay, so first of all, um, there's an update operation, right? If I had to brute force it, so let's take our previous example, 1, 2, 3, 4, 5, and then bunch of queries, and this first one, 2, 2, 0, 2. Let's take this for example. How would you do it if you had just one query? You'd first update it, so it'll become 1, 2, 2, 4, 5. Then you'll calculate all subarrays one by one, take their product, modulo k. If it is equal to this, you increase the count, right? Equal to this x value, you increase the count. You add another one. You update it again, 3303, right? This was the second query. Now you do it, you'd update index 3 as 3, so this will become 3. And then you do the same thing again. You take the product, this whole product, right? Check modulo k if it's equal to this value. If it is, count increases. Then you take this part, you do that again. Okay. One thing, if this is not 0, that means you're not removing an empty prefix. So suppose it was 1. Okay. Let's take 2 for example. So what they're saying is 2, 3, 4. So remove everything before 2, the second index. So you remove this. Now you got to do the same operation on this suffix. So after removing nothing, empty suffix, you'll have 2, 3, 5. After removing 5, you'll have 2, 3, and then 2, right? And you got to do this for product model, okay, and check if it's X and increase the count if it is. So that's the result array, like in the end. But this is not feasible when the constraints increase, right? So you got to update, you got to come back, check the product. Even if you find a way to not to recalculate the products every time, you'll still have too many updates, too many checking from which array to which array, and then you got to do it again. So in these type of cases where update is there and you have a range query, so it's technically a range query, right? So what they're saying is, tell me the number of subarrays which whose product modulo k in this range, whose product modulo k is equal to x, and before that update a value. So this is an update and range query. So the first thing that comes to your mind is segment tree, right? So I know my solution involves segment tree here. Now, usually in range sum queries or finding max, what do? You have two leaf nodes, right? You have two, three. So uh, zero, suppose the five values, six values, sorry, one, two, three, four, five, six. Okay. This is zero, one, two, three, four, five. Segment tree is basically 0 to 3. There'll be a node for 0 to 3, then, sorry, 0 to 2, then 3 to 5, 0 to 1, 2, 3 to 4, and 5. This will have 0, have 1, 3, and 4. Right? This is your basic segment tree for this array, right? So each node in this tree is basically representing a range. Now, for finding maximum in a range, what do? Like all the leaf nodes are the actual values, 4, 5, 6. For each merge operation, you just take the maximum of these two. If you're trying to find the maximum, if you're trying to find the sum, you take the sum of the children, right? So suppose you're finding max. This is 2. 2, 3 max is 3. 4, 5 max is 5. 5, 6 max is 6. 3, 6 max is 6, right? So this is general segment reconstruction. Now, the merge in this case is easy. So you have two leaf nodes and you uh, make take the maximum. It's an O of one operation, which is very easy to visualize, right? Now, this is the key idea that I took from Programming Live with Larry because I was not able to come up with that with it at all. So the idea here is, let's say the information contained in the nodes in these leaf nodes is not just an integer value. It's what is the so you had an range here. You had a range here. So this was suppose L and R. So after removing empty suffix, this is the product you're getting, right? After removing one, this is the product you're getting. After removing two suffix elements, you get this, and then this product. Similarly, with this node, you have the whole thing with empty suffix removed, the product modulo k with empty suffix removed, product modulo k with the one element at the end removed, then this, then this. Now, when you combine them, you're basically merging the ranges, right? So L1, R1, L2, R2. So your new range is basically L1 to R1, next element L2, and the last element R2. So you're merging this range. So this whole node contains, this merged node contains information about the whole range L1 to R2, right? Now, technically speaking, I don't care how the question is worded, but what it's asking is, tell me the product modulo k of all prefixes after you've removed a certain part, after you've removed some prefix with that start value. So if you remember, it was index value start and x. So after removing everything before start, so from 0 to start minus 1, you've removed it. Now the new range is basically start to n minus 1, right? So this is a range in itself. And what they're asking is, tell me all the products of all prefixes modulo k and check if the answer, how many of those have answer x, right? That's the question. So now if you think about it, when you merge these two ranges, can you really combine this prefix? Okay, can you combine this prefix and this prefix together in the new merged range? So can you combine these two? No, you cannot, because once merged, this won't be a prefix anymore. So it'll be something like you have bunch of elements in the new range. Uh, Sorry, you have bunch of elements in the new range. This part, like not the whole thing, but a suffix removed, an element from a suffix removed, was suppose this was the original L L node and this was the R node, right? So this denoted this part, leaving out this, and then this part denoted this. When you combined it, this is not a prefix anymore, right? Because there's a element that you're missing in between, and it's not a subarray anymore. So it does not make sense for you to uh, combine the information from this to this, or from this to this, or from this to this. The only thing that'll make sense now is if you take the whole array, this part, and combine it with all of these. Because this is starting from the start of this L2 to R2 range, and this is ending at R1. So there's no missed element in between. And combining this and this is still a prefix. Combining this and this is still a prefix, where only the last element is removed from L2 to L1 to R2 range, right? Same with this, same with this, right? So this is the key idea. Now, what are we trying to achieve with this? Suppose we have a bunch of products, right? So this suffix, this prefix part is nothing but we're trying to calculate product, right? And these values, these nums of I can be large. So going like very naively with this, we really what we're gonna do is keep an array. So this is let's call it a stupid approach to do this. So you have L and R. What you've stored is the frequency of uh let's just say we've calculated all the products. So in this range, this is the product of the entire range. This is the product of entire range minus the last divided by the last element. So leaving out that. Now this. Similarly like this. Okay. Now what we're gonna do is in we know we're gonna do every operation model okay. So instead of keeping the whole product, like all the possible values in the whole product, let's just say we're keeping values from 0 to k minus 1, right? It makes sense, right? Because this is what we're interested in. So these are the remainders basically after dividing from k. So what I'm going to do is keep a remainder array of size 5. So I did not show you guys the constraints earlier. So the constraints are k is 1 to 5, right? So the remainders in this case can only be from 0 to 4, right? This is what I'm going to keep. And in each of these, I'm going to keep the count of subarrays that have uh, that remainder. The product of those subarrays, modulo k, have these certain remainders. For example, uh, suppose we just have one element, so 56, right? My range was 0 to 0. And my first element, nums of 0, was in the original array, 56. So in that case, I'm going to store an remainder array something like this. So 56 mod k, let's say it was 3. How much is that? 54, 2, right? It's 2, right? Yeah, it is. So for a single element, what I'm saying is there's one element with modulo 3, whose product modulo 3 is uh, 2, right? So my information for that node will look something like this. I'll keep an entire product. So I'll have one information called the product of that range, the whole product, which is 2. So 56 into 1 mod 2, that's 2. And then a remainder array, the count of subarrays with that product modulo k as whatever the remainder is. 1, 0, 0. Now let's take the second element. So this is 0. Okay, this was the node for 0. So just remember the segment tree. The leaf nodes are the individual uh, elements themselves. So in this case, this was the node for node 0. Now let's say this next nums was something like 56 and 2, right? So in this case, the product is again 2. Let's just keep it 3 to make it a little different. And 3 mod 3, our k is 3. So 3 mod 3 is 0. So for this, my remainder array looks something like 1, 0, 0, 0, and 0, right? Now, remember this step while combining both these nodes. What are we trying to do? So, what I'm saying is, I took a bunch of uh, prefixes starting from start, all the prefixes. Uh, in this node, I calculated the product of this, the whole range, modulo k. I saw it was something like 1 or 0. So I increased this count to 1, right? The zeroth index to 1. Similarly, for this, for in this case, it's just a single element, so you won't have any of these. But like, I'm just calculating for each prefixes the product modulo k. Whatever the remainder is, I'm increasing the count of that remainder by 1. Okay. Now, similarly for this node. Now, as I told you, a prefix, when you combine the ranges, the only prefix that will make sense are these, this, also this plus this plus this plus this, and so on, right? These are the only prefixes that will make sense. Otherwise, it's not a prefix. So if you try to combine this with this, there's an empty space in between. So it's not really a prefix. Now, again, I only need to, so this was the reason why I'm keeping track of the product. So when I'm combining two nodes, so this is trivial because this is just one element. But when the ranges increase, I want the whole product, right? So that I can multiply it with each of these remainders and see what the new remainder is. So uh, let's say my product, this right node had after certain iterations gotten 1, 0, 0, 0, and left was 4. Sorry, left prod was 4, and this was 1, 1, 1, right? So what this is specifying is in this L1 to R1 range, there was one subarray with whose product modulo k was 1 subarray whose product modulo k was 1, uh, sorry, for product modulo k was 0, product modulo k was 1, and then 2, and similarly for this. Now, I'm just gonna multiply this product with the remainder for each of these, right? And that, so let's say new remainder is left prod into I being iterated from 0 to 4. This is the new remainder. Okay. Uh, so all the prefixes from earlier stay. So this is still valid because these are all prefixes of the larger range as well, right? L1 to R2. So these prefixes are still part of this range. So at least 1 1 1 of each remainder still exists. So one subarray whose product modulo k was 0, 1 for product modulo k equal to 1. So these still stay, right? So my new node will look something like 0 1 2 3 4. It at least has this for sure. So it has these many subarrays whose product modulo k is each of these remainders. But there's some additional thing. So what is that additional thing? It's this part, right? So you know for why am I doing this left prod into I is basically so you have like product of earlier array into whatever product there was some subarray whose product was 1. Product modulo k was 1. So this was 2. So the combined of these 2 into 1 is still modulo k. Modulo k will be 2, right? So that's what we're trying to increase. So it'll look something like this. The second part, I know it's not really clear, but maybe if I write down the code, it'll make a little more sense. So let's just say new node dot remainder I equal to left of remainder I. So this is that base case like where at least one subarray of each remainder still exists. Okay. But also now I'm going to multiply the left prod with each of the remainders on the right. So let's call it new remainder. That's left dot prod into I modulo k. Right? Now new nodes remainder arrays, new remainder will increase by how many ever counts were there earlier for this, right? Do you get the idea? So if there were two subarrays with certain product modulo k as 0, right? Now if I multiply the left product with each of these, it'll give me two new arrays with some other uh, product modulo k, right? So that's some other product modulo k is new remainder. So in that case, I'll increase the new nodes remainder of new remainder by right remainder dot I. And this is the entire idea of the problem. So at each node, I'm storing two pieces of information. The product of the whole range, which that's because I needed to combine these two nodes later. And for each remainder, I'm calculating how many subarrays are there which give that remainder from 0 to 5. Uh, I think it should be clear. So just to reiterate, you had a left array. This is the combine process. Okay, so L1, R1. This was the product of the entire thing, modulo K. And you had in the right node list of remainders, the count of each remainder, like count of subarray which give that remainder modulo K, right? So let's say uh, these were the prefixes that we were trying to calculate for. So now this prefix and this prefix and this prefix actually for the product of this prefix, the product of this prefix and this prefix, modulo k gave me a remainder 2, 2, sorry. 2, 2, and 2. So this gave me 0, 1, 3, right? So for this node, the remainder array is gonna look something like 1, 2, 3, 4. The three subarrays which have product modulo k as 2, then what was it? 1. So one of these, 3, 1. Okay, this is also 1. And what am I missing? 1, 0, 3. Okay, makes sense. So this was the thing, right? Now, uh, multiplying this product by any of these prefixes, product of these prefixes, is gonna give me the same remainder, right? That is this new remainder part. So the entire range into the product of these three uh, subarrays, prefixes of right node. So this will give me a new remainder and it'll increase the count of new remainder in the new merge node. So this is our merging process. I hope it makes some sense. Like maybe if I code, you can see how we are going about this. Okay, so let's start. So the implementation is a little headachy in this case because you see it's segment tree, and then on top of that, you're supposed to take care of a lot of variables. So let's start with creating a node, right? What a node will be. So you have the product of that range and a remainder array. I'm just gonna like you don't need it to be of size 5 because suppose if the k given is 4, you don't need size 5, you just need 4, right? But without the loss of generality, it's gonna give the correct answer anyway. If you work it out, you'll figure this out. So I'm just gonna declare remainder to have 5 elements in it. So 0 for remainder 0, for remainder 1, 2, 3, and 4. The maximum case where k equal to 5. Okay, so this is my node class. Now let's define our segment tree. Okay, so this is just length, and then we'll have sorry, not int, node of size 4n, right? So I'm not gonna go over the basics of segment tree. So first step, all my operations are gonna be modulo k, so it does not even make sense to have earlier elements without modulo k. So I'm just gonna reduce them modulo k, right? Now I'm gonna try to build a segment tree. Let's write the code for that. Okay, now what all do we need during the build phase? You need the initial ranges, uh, the node value, the nums array, and k, right? So this is just basic segment tree code. Like if you guys look over it, you'll find it. If L equal to R, so we've reached the leaf node. In that case, I'm gonna create a new node whose product is the element itself, right? And then remainder of nums L. So originally I've done everything mod k, so this will be the remainder, right? So uh, basically it's saying there's one prefix in when there's only one element, there's only one prefix with that remainder, right? So this is one, and then I return. Again, very template like segment tree code, build L to mid, to into node, nums k, build L, sorry, mid plus one, R, 2 into node plus one. This is its right child, nums k. Now, usually in range sum queries or when you're finding max, what you would do is something like tree node. If you're finding max, it's math max, tree, uh, its left child's value or the max of its right child's value, right? This is what you do. But we can't have that here. We are trying to combine this remainder as well. So we'll write a different function called merge for this, or combine. Some people call it combine. And I'm gonna have the logic of uh, merge here. So merge in node in K. So now I know my left node is tree of, sorry, 1 second. And my right node is 2 into node plus 1, right? Uh, Again, basic segment tree code. So by the time I reach this node tree of node, I know its left and right would have already been like initialized. When you reach the base case, you would have initialized the new node. So I know these two things exist. Now my left product is left dot prod, right product is right dot prod, right? Now when I'm merging, I'm creating a new node. So my new node will basically have left prod into right prod. So the product of the entire range. So if you remember, if my initial range was L1 to R1, and then L2 to R2 was my right range. Now the new range is L1 to R2. So the product is left prod into right prod modulo K. So again, we're doing everything modulo K. Um, so this is the new node. So initial case. So the prefixes from the left node are still valid. So basically the counts in this new range, the way I'll explain it is in this new range, the prefixes which were part of L1 to R1, the L range, are still prefixes in this bigger range. So you'll have at least those many subarrays uh, in the new node, in the merged range, right? So this part of the code is for that. For int I k, remainder I is left remainder I. So whatever, how many ever subarrays are part of left range are still part of the new merged range. Now, to merge the subarrays from right range, this part of code handles it. So this is the new remainder, which is left prod, because we can only take the biggest subarray, like the whole array as a prefix from left range to be considered. Like if we take any sub prefix from the right range, it has to merge with the whole range of left. Otherwise, it's not a prefix anymore. Okay, so tree node, remainder, new remainder. I hope this is clear. I know it's a little technical, but if you like whatever I told you in the visualization part, if you see through it, it'll make sense. And if you just compare it to the code, it'll make sense of why we're doing this. So this is my merge function, right? Now next, we need update as well. because we are going to update at some point. Like if you remember, this first index value is the update in that segment tree. So let's go ahead with update. So what do we need in update? We need the range. We need the query range. Oh no, that's not query, sorry. So you need the index and you need the value to be a value which you need to update it to, the current node, the nums array, and the k. So if L equal to R, this is very much like the build case in segment tree. Tree node will now be changed to a new node with the new value. Again, modulo k. So if there's 36 and k is 3, so you don't need that 36 information. You just need 36 divided by 3, right? And the remainder of val modulo k will become 1 and you then return it. This part is again basic segment tree template. And if idx is less than mid, you go to the left part to update. And mid idx val 2 into node is the child, left child, and nums and k. Else update mid plus 1 or idx val 2 into node, the right child, plus 1. Okay. Again, you're supposed to use this merge operation that we just wrote the logic for that. Right? It makes sense, right? Because you're not just doing a very basic operation like adding or finding the max. So this is our update operation. Now let's try to write down for query. Now query is a little more complicated than how you would handle it in uh, normal range sum queries, because in range sum queries, the information that you're extracting from a node is basically just single value most of the cases, right? So you're either going for sum, so left sum and right sum, and then you add it together. So you don't really need anything else. But in this case, we need the whole uh, node as the information. So you can't just have one value being passed above. You'll have the whole node being passed above. So let me try to show you what I'm saying. So in this range, suppose, where's my segment tree? Okay. So suppose the query was for range, what is this? Query was for range 0 to 3, right? So you know this whole node will get, or the value from this whole node is supposed to get returned, and this, right? But it's not just one value. You need the uh, remainder array for this, and you need the remainder array for this. So query in this case is not trivial anymore. So what I'm trying to do is return the whole node itself. So when you get to this, you'll return the whole node. So you'll get this as the right node, and then this as the left node. Then you'll do a merge operation on this, and this is what your answer will have. So you'll get your answer from the remainder array of this combined node. Okay, so as I said, it's not trivial where you can return the integer itself, not much query, right? So you need the left range of query, right range of query, the node range, right? The node itself, nums array, and okay, again, basic segment tree code. Just like revise it once if this is confusing. It's nothing different from a normal segment tree template. If L is greater than QR and an R, okay. You return the tree node itself, right? So I'll query the left child and then the right child. And then I'll return. So now I'll write a new merge function because I want to return a whole node itself. And again, it's not trivial where I can just maybe add or multiply this left and right information. It's not so basic. It's the information is contained within it. So I'm combining these left node and right node. So I'll write a new merge function for this, which will return me a node, my this node. Where was I? Okay. Okay. So, no. Uh, okay, this is merge function, right? So node new. So I'm creating a new node with the product of both left and right's product. So it's left dot prod into right dot prod model. Okay, it's the logic is the same as the original merge that we wrote. It's just I'm returning a new node instead of a void value. Um, it's the same logic. So the prefixes of left range are still valid. So this new node's uh, remainder count is at least gonna be left's remainder count. On top of that, it's gonna be the whole product of left range, whole product of left range, left dot prod into I, like whatever is in the right range. And then new nodes, remainder of new remainder is gonna get added with right's previous remainder, right? And then I return the new node. This is my merge with some value returned on it. Now our original question is very easy just using these functions. So I'm building from 0 to n minus 1 nums k. Let's say this is the query's length and my result array is the same as query's length. So this is the first value is the index value. Second is value, what you need to update it to. Third is start, I 2, and then last is x value, right? Now my answer is just gonna be you query for it from start to n minus 1. So this part is just saying I've removed everything before start. So I've removed the prefix first. So if you remember the original question, you're supposed to remove everything from the start and create a range start to n minus 1. So this is my range. This is just my range. Uh, Search on the entire range. This is my current node value. Okay, sorry, here also I'm supposed to send a node value. Mm, nums k. Then this will return me the entire node with that remainder array as well. So my answer is X. That's it. And res I will become the answer. Return res. Yeah, so I think this should work if I have not made some stupid mistake. Okay, so because I'm returning null here, so left, right maybe null or left maybe. So if left equal to null, we return right. If right equal to null, you return left. So you don't need to merge anything. So it's just one node that's available, one range that's available. Okay, so what am I getting here? Hmm. Made some stupid mistake somewhere. Let's see. Mm, and I. So the problem should be in one of these merge operations, I'm guessing. Okay, let's see the first merge. This left, right, right equal to null, return left. New node becomes left prod, right prod, model. Okay. This seems okay. Let's check the other merge operation. Is also okay, right? Let's check the range is one like L to mid, mid plus one to R. Over there, very two into node. Hmm. Okay, so I think I forgot one thing. You're supposed to update before querying. So that's the issue, I'm guessing. Yeah. Yeah. So that's it. Thank you so much. And like if you have any questions, I know it's a bit confusing this whole problem. So if you have any questions, drop it in the comments. Thank you.